yours.
Thanks a lot, Jan, and thanks a lot to you all for joining. So I hope I can present you an interesting topic. I will do my very best. So, okay, you can see the screen?
Yep,
okay.
You can see it.
So the title of my presentation is Phased Arrays for Mobile Satellite Communications. Yeah, I will start with some words on IMST. I will just get rid of this here. So, somewhere here. So IMST, what are we doing? We are a design company. This means our focus is design, and because of this, from our 170 employees, there are 130 engineers. So it's a lot of engineering in our company. This is our core competence, engineering around RF and wireless systems. We have a classical business, which typically happens a bit in the background. So we are designing systems for our customers, and those customers bring it into the market. We are supporting this idea, this product from the early stage up to the production phase. And in addition, we have also some own products, but these are more software products or B2B products to support, let's say, development cooperations or some other types of cooperation. So that's how we work. And it's very typical that whenever we like to work on phased arrays, on other communication devices, but there's always a partner in the boat who is deep in the market and defines the specifications and needs from the market, and he build that system according. That's how this business goes. And as Jan already mentioned, we have been working since many years in active beam steering arrays. And we did this in very different technologies, and the applications were things like radar, satcom, 5G, and now 6G, where we're working on these electronically steerable arrays. Now let's come to our topic today. So I want to give you an overview on the background and the requirements. Then I will give some information on array basics, and then I will go a bit through the design methodology, the design process. How do you approach a certain application? Then, of course, I will give you some examples, and I will give some. So what is the background? And the background, I'm a real fan of phased arrays, and the background is quite interesting. And I can tell you, and I think you know, I put 3 examples. The first is Starlink. This is, of course, a very fascinating network, a fascinating constellation, with a lot of satellites. More than 1,500 currently, but much more are announced already, and they are very powerful in terms of communication because they have inter-satellite links. So even if your current satellite doesn't see the base station or the ground station, it will get data through the other satellites on a very high level. So it's a very powerful system, and and from there you can directly go down to Earth on any point, and the data rate can be very high. There's always this sentence up to. For sure, you will not always have the perfect data rate, but I would also. So broadband connectivity anywhere on Earth. Yeah, when we talk about mobile communication, we sometimes forget about the oceans, yeah, which is the bigger part. And of course, here for Starlink, there's no problem. So wherever you are, you will have connection. And this is true for you as a person at home, but also, and that's the interesting thing about, yeah, in mobile vehicles like cars, ships, and things. And another interesting story is the vision which is currently discussed for this network. The idea is really to have high nodes which are additional on top of the terrestrial base stations and which act a bit as a base station. It's not quite clear which functionality will be on these nodes, but for sure they will be somehow node in the network, and some of them will directly connect down to the terminals. And also, the idea is to have an automatic routing of calls through the next network. So ideally, you should not even know if you currently are connected to a terrestrial base station or that's the vision. It's still a vision. Please don't overestimate. Maybe something which comes into it. Yeah, but anyway, satellites are an integral part. That's new. Yeah? In 5G, satellites was a possibility. In 6G, it's an essential part, and the direct link to mobile terminals shall happen. Of course, there's still a lot of research to do, but anyway. And last but not least, the European Union is about to set up a European satellite constellation in order to have what they call independent connection for military, for governmental applications, but also for commercial applications. Yeah, and this is about to start in 2024. This is, of course, then in this moment mainly on already existing platforms, but then it should be further developed and fully operational. So, seeing these three examples, yeah, we have the chance of satellite coverage anywhere on the planet. So, excellent possibility for connecting mobile vehicles. And the good news for guys like me is always a key element is the terminal. Looking a bit in the requirements, very rough, yeah. When you look onto planes, how should a terminal antenna on the plane look like? For sure, we will need a high directivity in order to manage the budget and the high data rate, which is required. We will, for this reason, as the antenna is then, of course, highly directive, we need a beam steering and tracking. What is a very hard demand in aeronautics is low profile. So you have to keep the profile down so that you don't have aerodynamic issues and also, fuel savage and so on. So it's really a very hard demand. Yeah, on the other hand, aeronautics guys would like to have coverage down to low elevation. That's not easy to combine with the point above. Yeah, okay, but that's definitely a wish. And high MTBF is also a key thing, simply because you can imagine that maintenance in planes is a very expensive stuff. What I can also, on the other hand, say is that the tracking requirements are not so hard. So the movement of the plane relatively to the satellite is relatively smooth. Yeah? So no, of course there are some turns and things like that, not as hard as the other files. When you look onto ships, so antennas for ships, they have some similar requirements, but also some different. High directivity and high efficiency is, of course, important. Beam steering and tracking also. The form factor should be compact. Low profile is maybe not so hard as in the aeronautical case. Yeah. High MTBF is nice because ships go very far, and the problem is the system happens on the other side of the planet. So it's good to have a high relief and robustness. Coverage down to horizon is even more important because of the ship's movement and from the ship, the link to the satellite. If it's very low over horizon, it can mean that you have to go down to horizon or even. So, and the tracking requirements are somehow demanding. So due to the movement in the waves. Yeah, it can be not. Yeah, and the last example I would bring here is the car. It's of course currently now coming into discussion, even pushed by the OEMs, so by the car manufacturers, to integrate satellite communication into the cars. Yeah, one driver is autonomous driving, so the idea of having perfect coverage in any time. The directivity is probably medium. Of course, high directivity would be nice, but it's a matter of space. Yeah, beam steering and tracking will be required. Compact design is very important, and low profile is very important, but for other reasons, not for aeronautics, but primarily, first of all, for design reasons. Yeah? And the coverage down to low elevation is there, maybe not to zero. I would say no, because the low profile requirement is much stronger. And the requirements can be very hard in the land mobile case, yeah, especially for narrow beams. Just imagine you are not on the street, but in the countryside, and you drive through a hole. Yeah, in that moment, you have very high changes, very high angular changes. And if you want to have a perfect coverage in that moment with narrow beam, it can be it depends a bit how the system is tailored. Okay, some area basics before we go further. I think most of you know the principle. So the idea of the array is to make a linear superposition of single elements, which are placed somewhere in the space and have a specific amplitude phase. And by knowing this, this constellation, you can design a pattern. Here is the general case just mathematically described. So what is very important, and it's also a matter of the following slides, is that the E field is the product of the element of an element factor Fe times an array factor Fa. Yeah? So of course, you might have a large array and a small element, but this is important to know that this is a product. Yeah. So if Fe is 0, Fa can be very big and it doesn't happen. And that's important, and please don't underestimate. Fact, when you talk about radiation pattern, it's also a product of the element part and the array part. When you calculate the array factor, it's important to understand that you have to bring the amplitude and the phase of the single element into the array factor, because they do two things. The amplitude acts as a weighting of the element, and the phase, of course, contributes. So that's the basics. Now, the good thing is that when you come to industrial applications, things get easier because you prefer regular grids, and then the whole thing is simplified. The mathematics is more simple, and yeah, so the calculation is written here. Know it, and you can just describe the array factor via this sum here, and you can put the amplitude in front of the sum as it is constant in the case of the array. If you make a non-uniform amplitude distribution, which is maybe needed for lowering the side lobe level, then you introduce other distribution, not uniform, and then of course you need to put the amplitude under the sum as it varies for different n. So that's the only difference. For the rest, the structure. And the good thing and the fascinating thing about those arrays is the possibility of electronic beamforming. So you can introduce a phase shift delta, and this delta changes the main beam direction. And by this, you can go from maybe standard broadside radiation. And when you now start, so this calculation, this equation has to be built, and then you have this angle. And when you now start tuning the delta, you can change this beam without mechanical movement. That's the core of the experiment. Okay, now knowing this, the question is how to approach a certain application. And I will start with the system concepts. And I can tell you there are many concepts. These are the, let's say, the three main concepts. On the left hand, it's a switch. This is a very simple idea. Yeah? When you want to cover a certain spatial area, you can think of having several beams, which you generate by changing the orientation of a sub-area, for example, and then you simply switch between those sub-areas. And that's a very simple possibility to have electronic steering, and it's cheap, and it's also with very low loss. Yeah, this is a big advantage. So we did this several times. The complexity is low, but of course you are limited in the number of beams you can realize. The next step is then what we really call the phased array, which is done in the analog plane. So this means you have phase shifters on the RF plane. Analog is not, maybe in many cases, not a real good word, because it's, of course, phase shifter has also 4 bits or so, yeah, but it's it happens on the analog plane, therefore it's called analog. And the beam really is, by use of this phase shifters, you can have quasi-continuous steering of the beam. And of course, the most complex system is digital beamforming, where you really make the beam steering on the digital plane. And especially this technology allows you to generate multi-beam through the same aperture at the same time. Yeah? And this is, of course, very helpful. Just think of radar. Yeah, in today's automotive radars, we have a lot of digital beamforming as it increases your resolution through the same aperture. So. But we should all be aware that from left to right, there's a gigantic difference in complexity, but also. Now, when you do a 3D beam steering with the classical phased array, for example, you have to keep in mind that you might need a lot of components, phase shifters. So, for example, for a mobile terminal to a geostationary satellite, you might need 4,000 elements. So this means 4,000 phase shifters. This is quite expensive. That's very hard to integrate, and this might generate a lot of thermal issues. Yeah, so it's hard stuff. It's not impossible, but it's hard stuff, and it can be very complex and expensive. And the question is, do you always have to go this way in order to do electronic beam steering? Well, it depends. Yeah. So, for example, what we did is we had a closer look at vehicular movement. So, thinking of you're going around with a car and you track or you record the angular behavior, and you end up with a curve like this. Now you can take this curve, and then you can draw a blue line into this red curve, and then you can do a kind of subdivision. So you can identify a blue part of this movement, which is more related to when you turn the wheel, when you make slow movement, when you go into the curve, so the large angles, and the red part, which is mainly linked to vibrations. Yeah? And it's a strong difference in the behavior and the requirements. So the movement, which has to cover the vibrations, has to be very fast. So the compensation, the movement is fast, and the compensation of so high frequency, but only small angles. Yeah? And our idea was now to cut our system steering mechanism exactly in those two parts. And by this, we did what we call hybrid beam steering. So there is a blue part, which is maybe a turntable, which is mechanically, and it covers the blue the blue part of the curve. And in order to do this, it can be slow, yeah, but it has to be, it has to be able to perform large coverage, yeah. Whereas on the other hand, you need a red part to cover those vibrations, and this part has to be very agile, very fast, yeah. But the amplitude is not so large, yeah. And then you can combine this in that way that you make a mechanical turntable, for example, and then you make an on top a phased array, but not on the element level. So that's quite an interesting story. So mechanical steering for the slow movement, and electronic beamforming for very fast, very small, angular-wise small movements. And by this, you end up in a good compromise. You save a lot of components, and your life gets easier in terms of integration density and thermal. Yeah? We played a bit around with this, and you can kind of design your system exactly to this curve here, yeah. So this curve by defining the sub-array level. Yeah? So the more you go down, or let's say the smaller the sub-arrays get, the larger the scanning. And by this you can tailor the system what you need. The higher the level of subdivision, of course, the higher the scanning. And another very important point, what we learned, is that you need a modular approach. Yeah? So you need to, it's always a story about quantities and design efforts. And we learned to use, to design a module, a sub-array module, independent from the fact, is it fully electronically steerable or is it fixed beam, but it's just a module of 4x4 or 8x8. And then with this module, you go into different form factors in order to realize, for example, car or. So overall, when you approach the system, it's important to see we have to reuse modules whenever it's possible, and generally you can say you have to carefully tailor your system to the real needs. Yeah. So what we learned is the customer, of course, wants everything right away for no price and no weight, but going deeper into the details, you have to understand what is really necessary, which level of steering, for example, which steering speed, and then you can think of the right system, and you can tailor it, and then it gets interesting. Huh? Whereas if you want to do, any antenna or the perfect antenna for everything, it's very hard. But good news for us, we are engineers, so we always want to make something new. Okay, now let's approach the concrete aperture size and shape. Of course, these are the important parameters you all know: directivity, gain, EIRP, and effective aperture. And now the concrete question is to approach the concrete request. How should I dimension my aperture? And in order to do this, I just should say some words on the characteristics of these arrays with a very simple investigation, which this is an analytical tool, and this gives me the pattern for a given radiator. Yeah, and here you see a comparison. On the left side, it's an isotropic radiator. I took only the upper hemisphere. Of course, the isotropic radiator has spherical, in total, spherical characteristics. And as a comparison, I took a microstrip patch, which is mounted over a ground plane. So it only offers a half sphere. And in this half sphere, we have, of course, a preferred direction, which is the point of the directivity. So it's directly in broadside. The patch is here. In broadside, we have the directivity. In air, it's 7.3 I without losses. And when you go to low elevation, it gets down. In this theoretical case with infinite ground plane, it's 0, but in real life, it's not 0. But so that's the situation. And the isotropic radiator has the same weighting in all directions and the patches. Now, if you just, as an idea, put those two radiators into an array, we only look onto the upper sphere. Then on the left side, you see the resulting pattern for the isotropic radiator. It looks quite good. On the right side, you see the solution for patches with the same number of elements. And this is better. You cannot see it from the directivity. The directivity is higher, of course, but this is normalized. So you see it. What you see is that the distribution of the power is there's relatively more power in the main lobe and less in the side lobes for the microstrip patch. So this gives you a clear sign that this is better because you want to have, of course, main lobe. So in this case, of course, the microstrip patch is much better as the element has some directivity and the array also, both in broadside, and this is perfect. Now, if I incline now the beam, if I go to 30 degrees, this message is still true. Yeah? So the microstrip patch, the element factor is slightly lower, but this is not really dramatic. And therefore, the pattern looks even better. You see here, this is better for the patch. And again, you have the impression that there's more power in the side lobes. Patch better, but now, of course, if you go down to 60 degrees, the story changes. And why does the story change? It's obvious, but it's bad anyway. Yeah. So now the microstrip patches have still the directivity, but this goes for the single element in the wrong direction. It goes in broadside, and this damages your pattern in the side lobes. So it makes the side lobes larger, and the main lobe gets. Yeah, so here in this case, the isotropic radiator would be the better solution. But now I should already mention, which I have some more information in the next part. We cannot take the isotropic radiator. You cannot build it. Yeah, but also if you might think of, okay, why not taking an element where the directivity is mainly not in broadside, but to the horizon? And the answer is no, that's also not possible, simply because then you have very high. So I will come to this point in a minute, but for the moment, we have to accept that the microstrip patch will be the better choice. But then we have to cope with the fact that it gets worse when you go to. So that's important to know and to understand and to keep in mind when you now approach. Now I want to tell you some two things about the scan range. Yeah, I mean, maybe you know it, maybe not. We have many customers saying, yeah, I want a super flat antenna, which is on the rooftop of my car, but I want to have coverage down to horizon. Yeah, it's not possible. Yeah, when if the aperture is horizontal, there is a limitation, and you can imagine that, the effective aperture changed dramatically from broadside. And this has to be to keep in mind. First of all, you have to know that when you design a phased array, you do it for the worst case, and the worst case for the planar phased array is always the point of lowest elevation. Yeah? So your gain, your G over T and everything is designed for this direction. And of course, it's much over designed for this direction. So that's not nice, but that's how it is. Yeah. And the practical limit in our experience is between 65 and 70 degree. And then already you have a dramatic degradation in performance. Yeah. Maybe it's not so much in the signal, but in the noise. Yeah? So that's just the limit. So what you can do to overcome this, you can think of, well, then let's don't do a planar aperture, but something else. For example, a convex aperture. We also did this. There's a very interesting antenna in our house. If you come around, you can see it. It looks like a football, and here you can have a convex aperture, for example. And then, of course, if your desired direction is here, you have a significant part of the aperture available. And then you can go down to this direction without degradation. You can imagine that the effective aperture of broadside for this arrangement is the same as in this desired direction. So and the other case we also had in some applications is the inclined aperture. So this means you help a bit the electronic steering by pre-inclining mechanically. This is of course very helpful if you know the desired direction in azimuth. So if there is only a specific azimuthal direction, this is perfect. But of course, if you want to have azimuthal coverage of 360 degrees, then you might think of maybe having a turntable for this socket, and then turn around this. So it helps, but again, you need to think, is it worth or not? So generally, inclined or convex apertures allow for high efficiency at low elevation angles. But if in the case of convex, the aperture needs to be significantly bigger, of course, because you always use only a part. And I really advise you to switch off those parts because they only will generate noise in the desired direction. So at the end, you use only part of this in any mode. And the inclined aperture is helpful, but it's kind of linear. So every degree you want to go down, you have to increase, of course, your mechanical alignment. And what I also turned out in many investigations, also for ESA and some others, a bit of convexity or inclination doesn't help. So forget about having a small socket with some inclined elements. Either you make it planar or not. So that is our experience. The mixture is not. Okay, so now you maybe design a planar array. You negotiate with the customer a minimum coverage for 65 degree, and then you can decide. Now the question is, how do I approach a design? And the key factor is, of course, the element. And those parameters are important. Bandwidth efficiency, gain, coupling. I will go very quickly through that. Now the element is, for example, a microscopic patch. You know this very well. I don't go in detail here. It's small size, 2 polarizations. That's very helpful. Yeah, it's easy manufacturing, and it enables low mutual coupling. And now the problem of the element distance. Oh, when you have now a phased array, you have a certain element distance of A, and you have a phase shift of delta. You are able to generate your desired main beam. However, if your distance is too large, there might be a second solution for this equation here. And then you get the grating lob, yeah. And this is, of course, typically not wanted because it takes half of the power, yeah. And it looks in a direction which is unwanted. And if you calculate now the minimum distance that you can have for avoiding grating lob, I should say the grating lob is of course there, but the question is it visible in the half space or not? Yeah. And in order to solve this equation, and for the worst case of sine alpha is 1, you get this very famous factor lambda, yeah, half of wavelength. Yeah, what we typically try to have in phased arrays. This is quite common, but this is quite hard, yeah, in terms of integration density. And of course, the problem is the elements are very close, and the mutual coupling gets higher. So that's the problem. So the mutual coupling is a bit the other part of the story. Yeah. So you want to bring the elements close together to have a perfect pattern, but then of course suffer from mutual coupling. And you might do a lot in order to improve this because it's worth doing it. Yeah. The better, the lower the mutual coupling. And for example, in this case, we did a design which is in fact half wavelength spacing, but then in LCC, and we put the element into cavities and we build wire fences in between. So a lot of effort in order to bring down the mutual. So yeah, the performance of phased arrays depends on low mutual coupling, and the microstrip patch is a good candidate for this, but not the only one. You will see in my examples, there's no microstrip. Yeah, but still, what is the case? The element pattern limits the array performance close to horizon. So those elements who allow for acceptable mutual coupling are those who have less radiation over the horizon, and therefore, at the end, it will be difficult. Beam steering and tracking. This is an important topic. Please don't underestimate, because this is, of course, key to have the stable connection. If you have the perfect beam, but it looks into the wrong direction, it's not good, especially if you disturb the neighboring satellite. Yeah? I can tell you this can be very costly for you. So please avoid. We have two possibilities. You can do what we call open loop, which means we identify the right beam direction by just taking navigation data. This you can not simply use one compass or so, but it's more a complex arrangement where you today find very good solutions, also due to the further developments in drones. And so, yeah, there are a lot of things on the market, very cheap and very good, where you can use different measurement units, make data fusion, and then estimate to the satellite. We did this many years ago already with quite expensive components. And then we made a test. We turned around the antenna with sudden changes in the heading. Yeah, and it looks like the blue curve follows perfectly. But if you look into the details, it's not so perfect. You see, oh, okay, if you change the direction, the system gets a bit in troubles. And then it understands, okay, something has changed. And so it works, but it's also not. And the other concept is what we call closed loop. This means that you receive, that you have a test receiver on board, and you receive the signal from the satellite, and in any moment you check if this signal is okay, if maybe in other directions it would be better. That's closed loop, and that's quite good because we have feedback from the satellite. Of course, there's also here a disadvantage. One disadvantage, for example, is that in the classical way, if you think of a mechanical steerable dish, you always have to rotate around the optimum, we call this sequential rotation, in order to make the connection to the satellite. So you're never perfect, and your system suffers dramatically from always rotating. So maintenance necessary very early. So that's also not perfect solution, but the general idea of closed loop is good. Yeah? And it's not a surprise if I tell you that today we typically combine both. So we take open loop elements, but we also need closed loop. Yeah? Both systems have advantages and disadvantages. For a stable system, you kind of need they have, yeah, I can just give you an example for an advantage. If you have a closed loop on your yacht, you go down a channel and you are under the bridge, yeah, so the system gets completely confused. And those examples show that it's good. Okay, yeah, some examples which we did recently. This is an example for a hybrid steerable antenna for maritime applications. Okay. This is, it consists of a basic module. This module has 8x8 elements, and it's a fixed beam module based on waveguide technology, so very low loss. So you have a waveguide, a central feeding, then a waveguide network, and then you have elements which are not patches but small horn radiators. And they are done in layers, so we have different layers for different stations. And then we managed to convert this idea from metal into plastic molding. And by this step, we did a lot of things. So we saved weight, of course, and we opened up the perspective for low production costs. And electrically, we managed to be more or less equal because, you know, it's the modules are fully metallized, so no field is going into the material, and therefore it works like metal if the galvanic is good, and it is good in our case. So we are very happy with performance. And the manufacturing accuracy is also quite high, which is helpful because once you start, you know, polishing those elements, you will directly get shifts in phase from one module to the other. Yeah? So it's very good to just take them as they come from the machine, and then you have a very good array. And now what you can do, you can either use this for a large array in a fixed beam constellation with a back network, or you can steer this array on an element level in the idea of having a hybrid steer. And we did this now in one case for a maritime satcom antenna, where we implemented TX and RX modules at 20 and 30 gigahertz. This is not written here, so it's K-band, and combined it in a way that it's very compact and relatively small on the ship. And then we implemented a beamformer chip for the RX panel, which serves several modules. So one beamformer chip can do 2 channels times 4 elements. So 2 polarizations, for example, times 4 elements. And then you can have a small electronic steering, and we use this steering exactly for the sequential rotation. So the antenna looks stable onto the satellite, whereas this electronic beam curves around and checks direction. So this improves the MTBF and of course. Now this is a measurement from this panel antenna. You see the gain is quite high, 40 dBi, and this is the vertical cut. We have some, of course, some kind of grating lobes, yeah, which we cannot avoid to the subgrouping, but they are low enough. Okay, and this is a test of this antenna. Just imagine this is of course done on land, as you see, but we have here a window towards south where we see the geostationary satellite. This is the antenna, and now imagine this antenna would be on a ship and moves around with the waves. And here on the monitor, you see the signal to the Ka-band satellite. So you can see it's the weather is not so good this day, so there's a strong movement. But you see the antenna stays very stable, so the sequential electronic rotation works. Yeah? The panel is always in perfect alignment to the satellite, and the signal is stable. So this proves that this concept works. Oh. Yeah, this is already in the prototype stage. As always, we don't sell it by ourselves. Yeah, this is done through our technology partner, EPAC and IMST. They are building, let's say, the full device and integrating this antenna. And it's a very powerful antenna, and it's a very agile. And the second example is this array, which is a full-phase array. And here we made, again, this modular approach of 8x8 elements, where one element has a density of 25 dBi, but in this case, it's an active element. And the good thing is now, imagine you have a power amplifier behind every element, and you know the story, when you double the size of the array, you win 3 dB, but in our case, we win 6 dB, yeah, because we always double also the number of PAs, yeah, and that's the interesting thing. And people are, it's always interesting to see the customers, yeah, they, oh, you have so low power, but then you scale the array and you get dramatically more power through that effect. So the ERP can be very, and yeah, the basic module is again not based on patches, but on small horn radiators. But in this case, it's a layer stack of metal and organic substrate. So you have here this metal plane, then you have a substrate which contains also the feed structures for the horn antennas. Then you have a big block which is mainly cooling. And then on the bottom side, no, that's not true what I said. On the bottom side of this top layer, there are the chips. And now here is the back side, and you see again we use those new beamformer chips where we can drive 4 elements through one chip. So this is a beamformer chip. These are the corners to the 4 elements which are on the top side, and times 2 polarizations. So we have 8 ports. Yeah? And yeah, we designed this module, and here you can see the simulation using Empire of the top side with showing the rotational vector realized in these horn antennas. And on the bottom side, you see how the energy comes from the central feeding point of the module and then distributes in a hierarchical network to these beamformer chips. Yeah, and then we built also here this array. Again, we made a separation TX-RX for several reasons. It made sense. And this is already mounted on a mechanical shock table because it was prepared for a flight. Yeah, and then yeah, we made some electronic testing. And you see, this is the the electronic beam steering. Now, of course, we have a much larger scan range as this is a full array. Yeah. But of course, you see the degradation when you go down from the top, yeah, to the lowest elevation in that case, which is 45 dB. Then you see the gain drops about 3 to 4 due to the different phased array issue. And anyway, the test flight went very well. Yeah, the antenna was mounted in the nose of the plane. The weather was horrible. There was super strong wind, but connection was very stable. So this is my proud team in front of the plane. Yeah. Okay, so let me come to my summary and conclusions. You see, the mobile satellite communication gets more and more important. The phased array technology is a good candidate, especially when it comes to vehicular satcom terminals for different vehicles. Yeah. What we learned, and I think this is also true in future, you need a careful tailoring. Yeah. You cannot do everything in any array. You cannot use one array for everything. That's very important in order to save cost, thermal topics, yeah, size. So those factors have to be considered and have influence in the design. Yeah, hybrid steering is an interesting alternative if you need super high gain antennas, but only either a low angular coverage or you combine it with mechanical platforms in any way. And the full phased array, of course, gives you much more flexibility, but with the limitations that we saw when it's only. But anyway, let's say phased arrays will be widely used in mobile satcom, is my prediction. Okay, thanks a lot for listening, and I'm open for any questions.
Yeah, thank you, Matthias, for this very, very interesting talk. So to all people in the audience, there is this Q&A button that you should be able to see at the bottom of your window. So some of you already found it, and there are a few questions there. Matthias, do you also see that region? So
I see it.
maybe
Yes.
you can also read it, but for all participants, I would just repeat the single question, and then maybe you can briefly answer it. So so there was one question on the speed of beamforming, and the question is, how do you compensate for the ship vibrations and movement? Do you do this completely electronical, and is the beamforming fast enough for that purpose?
The steering, I'm not in the exact details of the steering, but I would say the vibrations on the ship are hopefully so small that they don't touch the angular range of the main beam, which is maybe in the order of 1 degree. Yeah. So I would, it's more the movement of the ship, and this will be in fact compensated mechanically, yeah, as the electronic is mainly used for the sequential rotation. Yeah. I'm not sure if the electronic is for sure fast enough to cover also vibrational issues, but I think it's simply not available as it's used for the sequential rotation. Yeah. You can think of, but I think in that case, it's concerning compensation. The ship movement is really mainly done. Which is, I should again say, it's not as hard as in the land mobile case. Yeah. So the maritime profiles that we expect, they are more like I've shown in the video, they are a bit smoother. Yeah. So it can be handled.
Okay, thank you. So then there is a question regarding automotive applications. So what do you suggest the antenna aperture size to be for automobile or maybe UAV antennas as well? So how small can it be?
How small can it be? I think I would expect simply for different reasons, for space reasons in the car, you cannot go significantly beyond 8x8 elements at Ka-band, for example. Yeah. You might. The story is different by looking at terahertz, of course, but for Ka-band, those 8x8 elements, which is already in the order of 8 centimeters by 8 centimeters, it's quite big. Maybe it's only 4x4. And then you have to cope with the link budget as it is. The good thing is you have good precision, especially when you think of LEOs, which in a dense network, so which you have typically in broadside or at medium elevation. So it should work quite well. You have no obstacles in between. It should be a good connection. And another part of the question is also very interesting. The drones, that's currently under discussion. But again, here, I would say it's also not beyond 8x8 elements, just for space and height reasons, which is also a critical factor.
Yeah. So maybe again regarding the speed. So I skip one question to come back to that later. But since you already touched low Earth orbit configurations, is the presented hybrid steering fast enough for this situation as well?
Definitely.
Yeah. Okay. Impressive.
It's it's from the steering mechanism. It's also optimized for those vibrations.
Okay. Okay, then the one I skipped refers to amplitude tapering. So do you do amplitude tapering in the design step as well, or maybe in the digital part afterwards?
Yeah, that's a very good question. So of course, in the case of the maritime antenna, we don't have amplitude tapering. Yeah? So the module itself is a uniform distribution, and our customer wanted to, I go back to this here for a moment. Yeah. So this is how the array looks like, and yeah, in fact, you have no tapering, yeah, and this leads to some issues in the side lobes. You profit a bit from the super high element gain, which helps you, yeah. But anyway, the side lobes are there. You can think what you can do is, if the module itself is only only a uniform distributed, so the submodule, you are limited in what you can do in terms of tapering. But what you can do is what we did in cut. You can use a diagonal cut. Yeah, so maybe you have seen some of satcom antennas which are oriented in that way towards the Earth, and the reason is then in the diagonal cut you have kind of a natural tapering, as you have less elements on the outer side and more on the inner side. And this improves your pattern. So that's a possibility. If you can, of course, with this array, you can also implement amplitude weighting. You cannot do for this. For this you can do, but for this you cannot. Yeah, for the first example you cannot, because this is from the structure a hierarchical network. It will always have a uniform distribution. You can think of steps in between the modules, but this will not give you a quasi-continuous distribution.
Okay, thank you. So then there is a question about the radome. So how do you account for the maybe the distortion of the field pattern? When the
it's a very critical thing. So I can tell you, especially in the case of the plane, of course we showed the antenna. We showed the antenna in the open stage, but we needed a radome for the flight. Yeah? And this radome made some reflections, and we ended up in a layered radome, which was designed in a way that you have just lambda/2 as a distance, so that any reflections are suppressed. Yeah, and this was the only solution, and it works only in our band, and in other bands, of course, it's horrible, this radome. But anyway, for our case, it works good.
Okay. Okay, and then there is a bit more detailed question regarding the steering. So thank you, Matthias, for the nice presentation. I have observed in your antenna field that you can steer the beam in elevation direction easily by keeping the steering azimuth plane to 0. But how can we steer in azimuthal direction by keeping elevation angle at 0? So
in the case of the hybrid steering.
I think so.
Yeah. Okay, I would say maybe this question refers to the principal example, which was given in the, oops. Is it? Yeah, maybe. So the question is whether you can keep the elevation direction while moving in azimuthal. Yeah, you can do it. Yeah? So it just assume you have an array, and by this array, you define the inclination. Yeah? To, I don't know, 30 degree of elevation, and then you turn the turntable and the electronics stays stable. This might work. Yeah.
Mm.
Yeah. The only yeah, maybe what is important to know is that this example is somehow a bit misleading because you know, we typically prefer to have both elements, so mechanical steering and electronic steering in both planes, so azimuthal and elevation. I have to maybe think of this example because it's not maybe a bit misleading, yeah, because it gives you the message that the curves only happen in azimuth and the vibrations only in elevation. This is of course not true. Yeah? So it's better maybe to if you look at this realistic example when you, for this maritime antenna. Go down. This one here is different, yeah, because those 8 elements, they all on the sub-array level, they all have amplitude and phase control. So now forget about maybe the sequential rotation. You can use this configuration also to compensate for vibration. As I said, I think it's not done in this case, but you can do it in both directions, yeah, in azimuth and elevation. So that is a better example, and that's also better in our experience. So not subdividing horizontal versus vertical, but subdividing in both planes the large movement from the fast and small angle. I hope this answers your question. And I will think of this slide. Maybe I should improve it.
Okay. Okay, and then there just came another question regarding the polarization. Is it linear polarized or circular for the Starlink dish? Do you know this?
For the Starlink?
Yeah.
I think it's circular as far as I know. And for example, this antenna can be driven in linear and circular polarization.
Hmm.
The circular polarization is typically preferred simply because it has it's direction independent. Yeah, that's one thing. So no matter what you do with your terminal on Earth, you will always be in the good direction. And also you have less reflection. So circular polarization is mostly used. The only exception is Ku band, and the Ku band satellites were often designed for house applications, yeah, where this factor mobile doesn't matter.
Mm-hmm. Yeah. So as far as I see, there are no other questions. Then thank you once again, Matthias. It was a really pleasure to have you here. Thank you for the very interesting talk, and yeah, see you soon.
Thanks a lot, Jan. Thanks to you all for joining, and yeah, hope to see you soon somewhere. Bye-bye.
Bye-bye.